I want to do a simple example now, looking at the vector description of rotation. Some version of this type of problem shows up on at least one of my tests sometime during the year. And so it really sort of looks at all the different components of this idea. So I have this bug, and this bug is on a rotating wheel. This wheel is rotating, say here, counterclockwise. The bug is at a distance zero point 0.2 meters from the center, we'll say. It has a radius of 0.2 meters. And it is currently rotating at a rate of 6 radians per second, which tells us that the angular frequency is 6 radians per second. And it is slowing down at a rate of 4 radians per second squared. And that tells us that the angular acceleration is -4 radians per second squared. You'll notice that in my verbal description, I didn't use the words angular velocity and angular acceleration. I said it is rotating at a rate and it is slowing down at a rate. And so you need to be able to understand, you translate that into our terminology of angular frequency and angular acceleration. Okay, so given that, I want to find the tangential velocity. I want to find the tangential, centripetal, radial acceleration, tangential acceleration, as well as angular acceleration. Well, I have angular acceleration, and I want to find the real acceleration and where that vector is relative to on my system, acceleration for my bug. Okay, so let's set up our coordinate system here. And so I see there, so here's the radius vector. I'm going to put a coordinate system here. So I have, if we say, I kind of have I'll give myself a right-handed coordinate system. Here's plus x and plus y with plus z then out of the screen. And so then I'm going to have a coordinate system at this instant of where the bug is, some radial coordinate system that points radially. I have a tangential coordinate system that's tangent to the circle in such a way that in my RTZ coordinate system, then there's a z that's also out of the screen. Okay, and so what can I say about the different aspects of this motion? Well, let's start with the velocities. Okay, so I know my radius already. The magnitude of my radius is 0.2 meters, and in fact, my radius vector then, I would say 0.2 meters. It's positive in the positive r hat direction in my RTZ coordinate system. So I have my angular velocity, which is 6 radians per second. It's positive, given the right-hand rule in my XYZ coordinate system. And so my angular frequency is here 6 radians per second. What about my tangential velocity? The magnitude of my tangential velocity is given by the magnitude of the radius times the angular velocity. And so I multiply those two together, I get 1.2 meters per second. So that's now the velocity of the bug at that instant in time. And it's along this positive t axis, so I could write the vector then has a magnitude of r omega t hat, or 1.2 meters per second t hat at this instant in time. Okay, so now let's go to the accelerations. I have a tangential acceleration, centripetal acceleration, and I want to combine that to find the full acceleration. So first, the tangential acceleration, we know, is the tangential component of the full acceleration in this coordinate system. So let's write that out. Let's recall that our acceleration as a function of time, it could be constant, but acceleration as a function of time, then is the radial or centripetal acceleration, which is the component of the acceleration on the radial axis, plus the tangential acceleration, which is the component of the acceleration on the tangential axis. And so these are components along this axis, so they can be positive or negative numbers. Okay, so the tangential component of the acceleration is equal to the radius times the angular acceleration. Well, we've already identified the angular acceleration, which is -4 radians per second squared. We know it's negative because we were told in the original example that it was slowing down, which means it has to be in the opposite direction of our angular velocity. And so that gives us 0.2 times our angular acceleration, -4, which is in 0.8 meters per second squared. Sorry, negative 0.8 meters per second squared is the component then along the tangential axis. So if I graph then that component of the acceleration vector, it would look like this. It would point along. It had a magnitude of 0.8 meters per second squared, and it points in the negative tangential axis at that point in time. All right. So now let's look for the centripetal or radial acceleration. So you can call it the radial or the centripetal acceleration. And that component is negative omega squared times r, as we found before. So that's negative omega squared is 36 times r, 0.2, and that gives us negative 7.2 meters per second squared. And so that's the component along the radial axis. It has a negative 7.2 meters per second squared. So if I were to draw that up here, it would be a vector much longer than our other vector. It looks like about a factor of 9, longer than the tangential component, and it points in the negative r hat direction. So that's the centripetal component of the acceleration. So now, if we want to go ahead and calculate the full acceleration, that acceleration then is equal to the radial component, negative 7.2 meters per second squared, r hat, then the radial direction, well, plus and negative, so let's call that negative 0.8 meters per second squared along the tangential axis. I can calculate, so that's the vector. I can calculate the magnitude of that if I want. And it's essentially 7.2 because this is so much larger. The magnitude, if I do the at squared plus ac squared, gives me about 7.25. So it's very close to the radial component. It's much larger. And so if I draw that here, it's going to be the sum of these two vectors. And it's going to be well, slightly larger, in fact, than the radial component. And so that is what the full acceleration vector looks like. It's the vector sum of the tangential plus the radial component. And so it points mostly towards the center, but with a small component in the tangential direction. And so this is how we can come up with all of our accelerations given the initial information of where an object is, how fast it's moving, and whether it's slowing or speeding up.